Thank you for joining today's discussion on building a financial transaction anomaly detector. Francesco and Maxime will guide you through the presentation. Since everyone is muted, should you have any questions, please feel free to type them in the questions pane. I'll be gathering them and we'll share them with both our hosts at the end of the session. Francesco, Maxime, the mic is yours.
All right, cool. Thanks, Amir. Good. So today's goal is to guide you through the process of building a simple financial transaction anomaly detector. So let me quickly give you an overview of the plan of attack here. So first of all, we want to understand the problem that we're actually trying to solve. So this involves understanding underlying concepts. We want to gain some insights into the problem that help us formulate requirements for the solution that we're going to develop. Next, since we're showing you this system using an example data set, we want to go through the steps of understanding the data set, which involves getting a sense of what could we use as inputs to our system, learning a bit about the distribution of the data, or at least parts of it, and maybe already formulate some hypotheses about what could constitute an outlier here. Then we want to create features, so inputs to our model. So we decide on which raw data fields we're going to use, as well as features that we're going to derive from existing data. Then we get to the core of our anomaly detection system, which is a machine learning model. So here we choose a suitable model based on requirements we formulated, and we try to understand the model mechanism, and then we look at the outputs of that model. And lastly, we want to guide you through the process of using an explanation model. And we'll of course talk about this more later, but for now it should suffice to know that this will help us kind of make sense of the outputs of our model. So first things first, let's start by discussing the important concepts and understand the problem well enough such that we can formulate requirements for our solution. So this presentation deals with identifying fraudulent activity within transaction data by means of anomaly detection. So the two concepts that form the basis for this presentation are fraudulent transactions and anomaly detection. So in the context of fraudulent transactions, we're dealing with a type of crime such as transactions stemming from stolen credit cards, for example, or money transferred to a criminal party by means of identity theft. It could also be something like accounting fraud and so on. So what all of these have in common is that they leave transaction records in a database that is mostly composed of normal entries. So the wish is to separate fraudulent transactions from legitimate ones, and anomaly detection represents a way of identifying fraudulent transactions. So anomaly detection refers to the process of finding outliers and in a data set, and where outliers for the purposes of this presentation will be defined as data points that are different from the majority of the data and that themselves constitute a minority of the data set. So this is just the definition we're going to use here. So to visualize the problem a bit more, we have some bad actors that perform illegal transactions, and those transactions leave records in a database. However, this database is mostly composed of non-criminal transactions from people who comply with the rules of whatever system the transactions are a part of. And the goal is to identify this minority of fraudulent transactions by means of running our database through some kind of anomaly detection system scheme. So the good news when identifying fraud within transaction data is that in many cases, we have all the data we need to identify this sort of crime. So there is no need to investigate and gather more evidence. The data is there. The bad news is that your fraudulent transaction is buried in millions upon millions of data entries. And on top of that, you might not necessarily recognize a fraudulent transaction when you first see it. So we really are trying to find the proverbial needle in the haystack. So how can we go about dealing with these challenges? In other words, what requirements for our anomaly detection system can we infer from these insights? Maybe the most obvious one right away is the need for automation, right? Because the sheer size of the data makes it impossible for humans to manually check all records. So at this point, you might think, well, if the problem is that human experts simply don't have the time to look at the whole data set, can we just try to automate their decision process? So if experts could compile a certain set of rules, for instance, transactions that exceed a certain amount are anomalies, or transactions that occur at time X that are of a certain type, Y should be considered anomalies, and so on. So any type of clearly defined rule to single out a fraudulent transaction. So if we have this set, so given a set of clearly defined rules, we could easily implement an efficient algorithm that flags all transactions that fulfill the rules that we defined as anomalies. And there's systems in place currently in industry that work like that. However, there are several problems with this approach. So first of all, coming up with a good set of rules requires a lot of work and expertise. So every rule needs to be validated and tuned specifically for the data set at hand. This also means that if anything about the data format changes, or if a different data set is used with a different distribution, the complete set of rules has to be reworked to reflect the new situation. And finally, and possibly most importantly, in most cases, it's simply impossible to predict all the shapes and forms that anomalies can assume. So a bad actor also has an incentive to not make the nature of his transactions completely obvious, of course. So to get back to our requirements, we have to address this problem of the unknown nature of fraudulent transactions. And for this, we basically can make use of the fact that we have plenty of data to work with. So what we want is we want to devise a system that learns from the data what constitutes an anomaly. And if we're talking within the paradigm of machine learning, we can also put the requirement that this model has to be unsupervised, meaning that when we train this model, we will not be able to tell it which transactions are anomalies and which are not, because we just come from a situation where we want to build a model and we want to find anomalies in our data set, but we don't have any information on them so far. So the idea of using machine learning is the following. So in the first step, we train some unsupervised model on our data set to learn about the distribution of our data and to get a sense of what an anomaly is in this context. In step 2, we can use this model to predict the likelihood of fraud for every transaction in our database using what it has learned in step 1. So notice how I said predict likelihood of fraud and not predict whether a transaction is fraudulent or not. So this is because the machine learning model will never be able to give us a definitive answer. So there's always inherent uncertainty in the answers it will give us. But we can actually take this fact to our advantage. So if we build a machine learning model that returns a continuous value as a kind of anomaly score that reflects the model's certainty about how likely a transaction is to be an anomaly, we can choose ourselves how wide we want to cast our net when looking for possible anomalies. So let me quickly elaborate on this point. So the output of our model will be a mapping from every transaction to a certain anomaly score, as can be seen in the tables. This score reflects how certain the model is that a transaction is or isn't an anomaly. And please note that if we have an anomaly score for every transaction, we also have an implicit ranking of all transactions in terms of how likely they are to be true anomalies according to the model. And we can also visualize the results of the model as a distribution of anomaly scores. So that's kind of represented on the right. So how will a continuous anomaly score and an ordering of the transactions make our anomaly detection system better? So here's again the view of the distribution. So the x-axis here represents all the different anomaly scores that were given to transactions in our data set. And the y-axis represents the number of transactions that received an anomaly score in the given range. This can also be seen as a ranking of anomalies according to their severity. So for instance, if lower value on the x-axis mean higher likelihood of being an anomaly, then transactions on the left of the diagram are the most severe. And we take this ordering specifically because it relates to our model, but we'll get to that. So if we want to consider some subset of transactions as possible anomalies, we have to set some threshold in the anomaly score. So for instance, we could say that all transactions on the left of this particular threshold will be marked as anomalies. And the continuous nature of anomaly scores allows us to adjust the threshold depending on how wide we want to cast our net. So let's keep track of everything. So let's add this to our list of requirements because as we have seen, a continuous output can be quite useful for flexible flagging of anomalies. The downside compared to if you remember the hard-coded rule approach that we talked about, so the downside here is that we might not understand why a particular transaction was marked as a likely anomaly. This is why we will add explainability as our final requirement for the fraud detection system. We want some way to understand why the model marked the specific transaction as a likely anomaly. So in the rest of this presentation, I will guide you through the process of building an anomaly detection system that fulfills all of these requirements. To make this as practical as possible, we will use a public data set from Kaggle to implement the whole pipeline to serve as an example, and to be able to show you some results at the end as well. So let's quickly look at this data set that we chose for the purposes of this presentation. So first of all, some quick statistics or some quick facts here. So actually, this data set is not real transaction data, but it consists of a set of simulated mobile payments. Now, you know, it might be obvious to you why publicly, it's hard to find real data sets that are publicly available for transaction data. This is a data set that is based on aggregated data from a real company, so hopefully it should reflect the real case. And it consists of more than 6 million transactions in total, and the fraction of fraudulent transactions here is 0.13%. And the simulated time span is 30 days. So here's a small excerpt of the data set, just the 5 first entries. And these entries are the ones we're actually going to use as inputs to our model. So we can just go over them very briefly, although the names should be mostly explanatory, self-explanatory, I mean. So the step field is basically the hours elapsed since the start of the simulation. So it's a kind of timestamp. The type field is just a categorical variable, assigns 1 of 5 types to every transaction. Amount is the amount transferred, pretty straightforward. Old balance original, new balance original, they're just the old and new balances of the account initiating the transactions. And the old balance destination and new balance destination are the same thing for the destination account. And actually the 2 fields on the right will not be used as inputs for a model, but they will allow us to evaluate our results. So is fraud is the ground truth for whether a transaction was created by fraudulent activity or not. And is flagged fraud is actually a result of a very simple hard-coded anomaly flagging scheme that I'll get into a bit more in the next slide. So if we look at this histogram, you can see that, and this histogram represents the amount, the distribution of the amounts of all the transactions. You can see that the vast majority of transactions are not very high when compared to the highest one. and transactions that are very high are outliers in the sense that there are not many of them. And just a quick reminder here, if you look at the y-axis, this is a log scale, so the difference in distribution is quite significant. So one way, or one very simple approach to flag outliers would be to set some monetary threshold where all transactions with a higher amount are flagged as anomalies. And so this is exactly the kind of hard-coded approach that I was talking about in the beginning. Even though it might work to some extent, its utility is limited and the approach is highly dependent on the data set. And this is actually the approach that they used here for this kind of is flagged fraud column. So this kind of just represents a very naive approach of flagging transactions. So, and they used some specific threshold value for this. But we can make this approach a bit less hard-coded by simply regarding the amount value as an anomaly score, where higher values imply a higher chance of being an anomaly. So we can move this threshold around, basically. And actually, this approach we will use as a naive baseline to compare our final model against. But more on that later. So now, before we get into the model, I'd like to, in this section, talk about the exact data that we used as inputs for our model, which we call features. So features are needed for every data point, and they can be seen as any type of explanatory data that can help to identify outliers. So it can be either taken straight from the original data set, or it can be computed based on other data, which we call feature engineering, which is super crucial since it provides a model with additional reference points to detect outliers. So the features that we use, so let's start with the ones that we just took straight from the data, which is the amount field, the transaction type field, although we did have to perform one hot encoding here, and the old and new balance values for both the destination and the origin. Now let's look into the features that we obtained by feature engineering, which is super simple, straightforward. So we just computed the change in balances for both the destination and the origin. We did that because we noticed that they don't always correspond to the amount field. So they do actually provide some additional information. Then the time of day, we just compute this by taking the modulo of 24 of the step field. And that's basically it. So that's all the features that we use. Again, feature engineering is important because, the model, machine learning is powerful, but it's not magic. So we need this part. And next, we're going to talk about the specific model that we used for anomaly detection. So for this, I'm going to give the word to Maxime.
Thank you, Francesco. We're going to talk now about the choice we made for solving this problem, and we're going to describe what is called isolation forest, which is our choice. So why isolation forest? Isolation forest is a tree-based unsupervised anomaly detection model. And the reason we choose this is basically because it fulfills all important requirements for our model that we defined earlier, except explainability. So if you remember the requirements earlier said by Francesco, it's automated, learn about what constitutes an anomaly from data, unsupervised, and continuous output. The explainable part will be explained later by Francesco. Of course, there is also some other models that could fulfill these requirements. So let's dig a bit deeper why we chose isolation forest in particular. So here are some reasons. Isolation forest is a classic to-go method without labels, even though, as I said before, the model does not by itself give us explanation for its decision. It provides a good basis for interpretation since its core mechanism is very simple and hopefully will become clear to you in the following slides. Also, the fact that this model reliably finds anomaly relies on two simple assumptions. Anomalies are few, and anomalies are different than normal entries. All in all, based on our past experiences, this is a good choice for the task at hand. And last but not least, there are many available implementations, and for example, scikit-learn. So let's come to the basic idea of isolation forests. In the following slides, we will try to give you an intuitive understanding of how isolation forest finds outliers. The core idea is that the anomalies are easier to isolate than normal data points. What does it mean to be easily isolating? We split the dataset based on random decisions. We keep doing this until a particular point is isolated. So you can imagine that if the point is very different from the others, it will not be in the bigger part of the cloud of the points, meaning that easy to isolate means a low number of required decisions. But this is worth, and we're going to show you a bit more concretely in a simplified version of isolation forest in 2 dimensions. But keep in mind that the low number of decisions is easier to isolate and is likely an anomaly. So let's imagine a list of all our transactions where we focus on 2 features. Here, all balance destination and the amount, and the transaction number on the left. We will look at 2 transactions whose values are displayed in the table. So the transaction 754 and 1219. To the right, you can see a scatter plot of the 2 features of all of the transactions. So once again, here you have only 2 features, and keep in mind that the space will be multidimensional. It's just for the sake of simplicity. Every dot here corresponds to 1 transaction. So if we take a look at the 2 highlighted transactions and we call transaction A and B, you can see that transaction A is far away from most transactions, meaning there are few transactions similar to it. Transaction B is close to a large cluster of transactions, meaning there are many transactions like it. So to a human, it makes intuitive sense that transaction A is much more unusual than transaction B. So we would like our anomaly detection system to get to the same conclusion. Let's first focus on point A and look how the core algorithm of isolation forest treats it. The first step of the core isolation forest algorithm is to select a random dimension and a random value. So here we have 2 dimensions, x-axis and y-axis. That way we make a random decision about how we split our dataset. In this particular case, a dimension has been randomly chosen, and the dimension is all balance, x-axis. And the value which has been chosen is around 250,000. So here it's 0.25. You can see here. Next, we disregard all data points that are not on the same side of the decision boundary as point A. So all this left side of the vertical line are eliminated. Now we repeat the process. We have a second random dimension and a second random value. Here, the y-axis and the value 2.5. And we disregard again the points which are above the line and Here you had just 1 point, basically. And we keep doing this until point A is isolated. You can see also that here we count the number of decisions. And to go back to point A, we took 7 random decisions. So now let's have a look to point B. We again choose a random decision and random value along that dimension and split the dataset accordingly. And it's exactly the same process as point A. Decision number 2, 3, 4, 5, 6. And you can also already sense that intuitively you're going to take more decisions than the point A, because B is in the middle of, I mean, not in the middle, but very much nearer to the main cloud of the data point. And here we took 14 decisions until isolation. So as a result, we have here that the isolation forest, in fact, is repeat the process you saw above many times. Each individual number is produced by one random decision tree. Here you see 3 random decision trees, but in practice, at least 100 are used. The average of all these scores form the basis of the anomaly score. So in the first example, the point A, you can see the first decision we had was, the number of decisions we had was 7. And here the second one is 10, and the third one is 6, and you repeat that 100 times or more, and you do the average of the decisions, and you get a score of 7.7. Let's keep in mind that the lower the score is, the more probable that the point is an anomaly. If we take the point B, here same we have 3 different examples. 14, 19, and 15, the average at the end is 16, and you can repeat that hundreds times, and here the score is 16, meaning that the point B is maybe not an anomaly like the point A. And the point B will be much more usual in the distribution. So this is what the generalization for it looks like. Of course, with a reduced number of random decision trees displayed here. So you have to keep in mind that you need much more trees than we just show you before to get a valid score, I mean, the valid number of decisions. In the original paper, there is also a normalization procedure in place to get from the average number of decisions to the final anomaly score. But this is not important for this presentation, since normalization does not change the ranking of transactions based on anomaly scores. And now I would like to hang up again to Francesco for the setup of our algorithm.
Thanks, Maxime. So far we have discussed the data that we use, the features that will be created, and we also discussed the model that detects the outliers. In this section, I'd like to quickly discuss some details relating to training and the evaluation of the model that are still left open before actually going into the results. So let's look at the setup we used here. For training and testing, what we did is we trained our model on all data, more or less, and we test our model on all data. Now, why can we do that without overfitting to our data? Well, we can do this because we're not using any labels. So that way we don't run the risk of overfitting our model. Also, we just use default parameters for the isolation forest hyperparameters. Then for the evaluation of our model, we used area under the ROC curve. So we use this particular metric because it's very useful for models that output different confidence scores. And that's exactly what we have in our case. And to compare our model, or to kind of get a sense of how good it is, we want to compare it to some baselines. So the first one is random guessing. So if it's not better than that, then we're doing a terrible job. And secondly, we're also comparing it to a naive anomaly score. And this is exactly what I discussed earlier, which is that we simply take the amount field of the transactions and we treat it as an anomaly score, where higher scores indicate a higher chance of being an anomaly. So this is kind of the reverse situation, as opposed to the average number of decisions in a isolation forest. So let's jump into the results. So first of all, here you can see the histogram of the normalized anomaly scores for every transaction of our data set. So remember that transactions to the left with lower scores are likelier to be anomalies. As you would expect, most transactions are in the high range of anomaly scores, meaning the majority of transactions are quite normal. But what's most important here is not necessarily the exact shape of the distribution, but the fact that we have now a ranking from most likely to be an anomaly to least likely, so from left to right. So what we can do, for instance, is to look at the top 5 transactions that our model deemed as most likely to be an anomaly. So basically the first 5 entries in our ranking. So let's take a quick look at them. So if you look at the amount field, so third field from the left, we can see that they're all very high amounts. We can also see, if you look at the old and new balances of the original, of the origin account, you can see that there's 0, which is quite strange. And also, you can see that if you look at the step field, all these transactions occurred during the same hour. So clearly, these are kind of strange transactions. But if you look at the is fraud column on the right, second from the right, you see that they're actually not fraudulent transactions according to this system. So you might think, oh, wow, our model must be super bad. Out of these 5 suspected transactions, none of them are a hit. But remember, we're dealing with a data set that contains only a fraction of 0.13% anomalies. So we have to take a broader view to evaluate the efficacy of our model. And to evaluate the performance of the model in general, we have to look at all possible thresholds at the same time, which is exactly what the ROC curve does for us. So here is the ROC score for our isolation forest, our naive baseline, and the random guessing baseline. So our isolation forest approach is obviously better than random guessing, and is also much better than the naive baseline system discussed before. Still, what you can notice is that the baseline is also significantly better than random guessing. Of course, this has to do with how the data set was created, but on some basic level, it also makes sense because in most cases, there would be no point in committing a crime for only a few cents. But of course, if the criminal knew this anomaly detection rule, it would be very easy to circumvent it. But anyways, so to summarize the results here, we can be quite satisfied, especially considering that we have done no tweaking of features or model parameters, model hyperparameters rather, whatsoever. So as a out-of-the-box, first kind of performance, this is quite good. And so just as a quick reminder, since an anomaly score does not tell us much about why a data point was deemed to be an anomaly, we want to create an explanatory model in addition to the isolation forest to help us interpret the results. And for this, we choose SHAP values, which are based on Shapley values from cooperative game theory, but this mathematical background is not too important. So we'll just kind of try to give you a sense of what these explanations values can do with an example. So here's actually one explanation for the anomaly score given to one transaction. Now there's a lot on the screen, but please bear with me. We'll walk over every part of it. So what you can see here is the anomaly score, non-normalized, that was given to this transaction. So this is really just the average number of decisions that it took to isolate this point. So basically, it's not determined. So just to kind of reiterate, it's not predetermined whether this is an anomaly or not, because that will depend on the threshold we set. But for now, let's just try to clarify the explanation process of how we get to this particular score. So this is the anomaly score that we get for this transaction, and here is the base value. So what the base value is the average anomaly score overall considered data points. So what we want to explain is how to get from the base value to the anomaly score, which is what the blue and the red bars show. So in other words, what we explain here is why did the model not just predict the average value? And this can, of course, be very useful to see why a decision was made and to check whether this behavior is expected. So if you look at the blue arrows, these are features contributing to a lower anomaly score. So specific features in this case of our old balance original and new balance original all made this specific data point more of an outlier. Because remember, lower score means more likely to be an anomaly. And red arrows, on the other hand, are features contributing to higher anomaly scores. So in this case, type and change balance original assumed values that can be seen as quite common in the data set that make this particular data point more normal and less likely to be an anomaly. So 3 general points I want to add regarding the explanations that are provided by this model. So explanation values provide local explanations for model predictions, meaning that we get an interpretation of one data point and its output at a time. And what explanation values tell us is how much every feature of the specific data point contributed to its output. So every feature of a data point has an associated explanation value. And lastly, if we sum all explanation values together, we get the output of the model minus the expected model output, which again is the average model output over the training set. So basically what we explain is the delta of what we got and what we would expect with no information about the input. And again, whether a specific anomaly score implies an anomaly or not depends on the threshold we set, but what we get here is a type of anomaly severity that is explained by these SHAP values. Now, you could imagine this could be very useful to decide whether a decision that the model made was valuable. For instance, let's say the model detects an anomaly, but the reasons for coming to that conclusion are deemed irrelevant by the experts. Then, it can be disregarded. Similarly, if our model comes to the conclusion that a certain data point is not an anomaly, the explanation model will tell us why this conclusion was reached. And then, if experts look at the reasoning, they can check whether this reasoning was indeed valid. And so this can also be very valuable for sorting out false positives. So let's take a look at some of the explanations we get. So for example, if you remember, we looked at the top 5 anomalies that are model detected. If we actually look at just 2 of them and show their explanations, this is what they are. So what's striking about them is basically that it's high amounts all around that are used as indicators for significant anomalies. So both the transferred amount and the original and new account balances are very influential here. But of course, this is kind of similar to the naive model, because the naive model is also using the magnitude of the amount transferred. But of course, we know that our model is doing more than that, because it is doing better, as we have seen before. And of course, here we're only looking at 2 specific transactions out of the 6 million that were given an anomaly score. So how can we look at how our model functions in a more general sense? Like how can we look into its inner workings? So essentially, because as I told you, the explanations are local explanations. So how can we get a general view? Well, basically, we can acquire more global explanations by aggregating many local explanations. So the purpose of this plot is to show how the change balance destination feature affects model outputs in general. So what we're looking at here is a scatter plot of transactions where every dot represents one transaction. And the x-axis represents different values for this specific feature, while the y-axis shows us what explanation value is attributed to this feature for a given transaction with a certain value of that feature. So what you can see is the higher the value of the feature change balance destination is, the lower its explanation value becomes. So the more it becomes an indicator for being a likely anomaly. Actually, large deviations from 0 in both directions seem to be indicators for anomalies in our model. But our model doesn't treat features separately in isolation, so it's often useful to keep an eye on features which can be done very nicely with the SHAP dependence plot. By the way, so SHAP is both kind of a mathematical framework of generating explanation values, but it's also actually a library, and I encourage you very much to check it out. It's open source. So what this SHAP library provides us is this nice dependence plot where we can see kind of the interaction with a different feature. And now this feature is kind of indicates whether this transaction is of type cash out or not. So transactions of type cash out are marked in red here and all others in blue. And we can see that although we have the same general trend for transactions of all types, if we single out cash out transactions, we can see that deviations from 0 have a stronger immediate effect than for other transactions. Let's take a look at another example. So here we plot the explanation values for different values of the hour feature. And again, lower values on the y-axis represent feature values that contribute to a higher likelihood of being an anomaly. And we can see that certain times of the day are much more unusual than others. And looking at the interaction plot with whether a transaction is of type payment or not, we can also see that while an hour feature between 0 and 5 is generally indicative of being an anomaly, this effect is even more pronounced for transactions of the payment type. Interestingly, this effect is not there or even reversed during other times of the day. So, but what do we have here? What's the point of these plots? So what you see here is basically a way for us to peer inside the model and understand some of its decision-making processes. So this is how the model works when it gives an anomaly score to a transaction. And what these insights allow us to do is to determine whether this is actually the behavior we want from our model or not. And to illustrate the fact that we might not want the specific behavior, let's look quickly at how our model treats the old balance original feature, which just represents the initial account balance of the initiator of the transaction. So we can see that higher balances contribute more to the transaction being an anomaly. But is this actually something that we want? Do we want our anomaly score to be a function of how rich the sender of the money is? Well, I'm no expert on the exact nature of this data set, but let's just say, for the sake of this example, that this is not the case, so we don't want this behavior. So what do we do about this? Well, basically, features that don't help us identify anomalies in a meaningful way, we should just remove them in a lot of cases. And just as an experiment, I tried this, and so we removed this feature that we're talking about, and it seems to be actually accompanied by a better AUC score. Just please note that feature selection is not actually part of this whole presentation, because if we were to try out many different combinations of features systematically, we would have to do this by creating a train test split to not overfit to our training data. So please take this result with a grain of salt as well. But we included this example just to give you an idea of how you can also use model explanations to get actionable directions in terms of how the model could be improved from here. Because basically what explanations do is they show you what your model does, and then you decide on whether this is what you want or not. So let's recap what we've done in this presentation. So we've identified the problem of fraudulent transactions in the real world and how anomaly detection could help us identify them. We've looked at the data set, and we've tried to understand it in terms of what's available and what distributions are we dealing with. We've discussed the features that we created, both in terms of raw data features and feature engineering. We've explained the anomaly detection model, its core mechanism, and why we chose it. And we have introduced a simple explanation model that can help us make sense of the outputs of our model. Now, to conclude, maybe let's take a step back and talk about how AI systems similar to the one we built are currently being used in the real world, in real businesses, in a general sense, and also with a more specific example. So here's the broad view. So across all kinds of different industries, there exist large databases of transaction data that contain patterns, and AI can be used to recognize those patterns and recognize deviations from expected behaviors. And this can be achieved in real time. So upon detection of a likely fraud, a transaction anomaly detection system could automatically reject a transaction. It could flag it for further investigation, or it could give it a ranking in terms of severity so that experts can focus their work on the most important anomalies. So as we have seen, AI systems can also provide explanations for their decisions, which helps reviewers to quickly evaluate a decision that the system makes. And for advanced systems, some advanced systems, which does not include the one we built, they can also incorporate more direct feedback from the reviewers that helps the model to become more accurate. For example, you can punish a model for flagging a normal transaction, or reward it for flagging a transaction that was indeed fraudulent. So that's kind of beyond the scope of the approach we discussed, but those are all kind of possibilities, and that's kind of what's being done in the industry. And let's take now a quick look at a real-world fraud detection use case that we at Unit8 have some experience with. So in some cases, it makes more sense to flag transaction parties based on their transaction behavior rather than flag individual transactions. So this is, for example, the case for traders in investment banks. So what investment banks would like to achieve is to flag so-called rogue traders, which are likely to commit fraudulent trades, which leads to all kinds of problems to the bank, such as huge losses, a negative impact on the bank's reputation, and the need for regulatory cash reserves. And at Unit8, we have experience being involved in creating a solution for this problem in the form of a data-driven anomaly detection of rogue traders, which created various business benefits, such as lower risk of rogue trades, protection for the brand reputation of the bank, and it also lowered the need for regulatory cash reserves. So this use case differs somewhat from the anomaly detection system that we built in this webinar, in that it flags traders as anomalies and not individual transactions. But many of the underlying principles applied here are actually the same as we saw earlier. So I hope this gives you a glimpse of the possibilities of AI in fraud detection. And since we've reached the end of our presentation, I hope today you acquired some knowledge that will help you build your own anomaly detection system, or at least, have gained some understanding about how these systems can function. And that's it. Thank you very much for your attention.
Thank you, Francesco. Thank you, Maxime. We've had a couple questions, so I'm going to share them with you. The first one is, would you consider that the aim of the isolation forest model is to, and the algorithm in general, is to minimize false positives, so legitimate transactions that are identified as fraudulent, or to minimize undetected frauds? And I think you've already touched on that. Wouldn't that involve some level of human supervision and decision making?
Yes, absolutely. So let me just give my thoughts, and maybe Maxime, you can add to that. So I think you can definitely use this for both cases. Now this, I think, how you apply it is also a function of how strict you set your model. For example, if you only if you only focus your view on anomalies that have the highest scores, then you can easily filter out anomalies that might be irrelevant. So if you have a lot of false positives, this might give you a tool to really narrow down to the most essential anomalies. And I think this could be especially useful in combination with the SHAP explanation model, because you will also get explanations for the false positives. Like, you will get explanations along the lines of, okay, this is not deemed an anomaly because of this and this, and then you can look at that reasoning and you can say, okay, that makes sense. So the model does what I want. But of course, the best evaluation is always if you have actual ground truth values. But yes, so I think you can also you can use it for that. You can use it to kind of diminish the risk for false positives. And in terms of detecting anomalies that you didn't detect before, yes, I think definitely. I mean, as you see, you can always take a broader view. You can always set the threshold a bit more leniently. And I think this kind of model that makes no assumptions whatsoever is very good for detecting anomalies that you previously didn't think of, because it will look at all kinds of interrelations between the features of your data that you might not have thought of, because a human cannot possibly think of all possible combinations. I hope I could answer your question with that. Or you want to add something, Maxime, maybe?
No, it's okay.
Okay.
Cool. Another one, can the same SHAP explanation strategies be used for memory-based deep learning methods like STSMs or GRUs for anomaly detection?
So I guess what you meant is LSTM, or
yes,
maybe it was some typo. Yeah. So LST. So recurrent neural nets. Yeah, I don't see any reason why not. So SHAP is basically a mathematical framework about which kind of involves how to think of how should we define explanation values, and then there's ways of actually computing those explanation values. And the good thing about the model we used is there's an efficient way of computing explanation values for tree-based models. Now for deep learning models, it's different. So the way of computing explanation values will be different. But so there's no reason for why you couldn't be able to use it for LSTM and GRUs, as far as I can see right now, because there's also a black box approach where you don't care at all how your model works internally, but you just decide on the inputs and you look at the outputs, and based on that, you can actually compute your explanation values, or at least you can approximate them. So I think in the SHAP library, that's what's called kernel explainer. So I think you can use the kernel explainer on any model to approximate SHAP values. So you can also use it, as far as I know, I might be mistaken, but I think you can also use it on LSTM and group. Yeah.
Thank you. And maybe a last one. I'm unfortunately unable to share all questions given the time frame we have. A last one, and probably a tricky one. Say, imagine a use case where the fraudster, the bad actor, has an automated bot or automated scripts that run a magnitude, a high level, a big number of smaller value transactions. So do you have any opinion on how this could be tackled if we could tweak the model to be able to detect them?
Yeah, that's a very good example, and I think you've exactly kind of identified the weak point of isolation forest, because by design it sees transactions that are in a group of very similar ones. It kind of sees them as non-anomalies. So in that case, if you actually create a huge number of those transactions that are super similar to each other, then I think isolation forest will fail you, and I don't have a kind of tweak of isolation forest ready in my mind that could actually solve this problem. So very good point. So in that case, I think you might want to look at other types of models, or yeah, it's a good point, and I can't answer that in terms of a solution.
Thank you. So let's conclude here so that we stay within the original time frame. Thank you everyone for your participation and your questions on this webinar. We will soon be sharing a video of that webinar so that you can come back at it later, or also share it with other people that might be interested. And just to let you know that on December 10, we'll be running another webinar on a different topic. It's about time series forecasting. We'll be sharing, again, more news on the social networks very soon. Thank you, Francesco. Thank you, Maxime. Thank you, everyone. And I wish you all a very good day.
Thanks. Bye-bye.
Thank you.